Hello everyone. In this video, we are going to talk about what exactly a bivariate expectation is. That's really the only goal of the video. I'm in our section 4 note packet on page 9. And right away, the definition of bivariate expectation is given. So for a bivariate random variable, xy, with a certain joint density, we could find the expected value of any function of x and y as this quantity that's given in the equation. And so one really nice thing is that if you have understood most about what we've been doing with double integrals up to this point to find various probabilities, the idea of finding a bivariate expectation really isn't too different. So it's nothing like super different than what we've been doing for the last week or so that's great. There are also some properties here, a couple of which will be illustrated with some examples and a couple of which we won't get to until class. So let's jump straight into an example. And our example is that x and y are continuous random variables with this joint density function. Hopefully we've had enough practice now where right away we're going to sketch the support, so that will still be important for finding all types of bivariate expectation. And I'll go through it a little bit more quickly than in the previous videos. So we know x is less than or equal to 1. We also know that y is less than or equal to x. And so I'm going to pick a point here and figure out that, yep, that point is part of the support. So here is our support set. And so when we find the expectation, our first examples were asked to find the expected value of x times y. Seems like kind of a useless thing to find, but we actually will use this particular bivariate expectation a lot in the next few days. So it's used in the definition of covariance and correlation. And so what we're doing here is we are setting up a double integral, and I'll get to those bounds in a second. The definition up here says to first put in the function of x and y that you're interested in finding the expectation for. And so that is x times y. So again, I'm just kind of grabbing that. That gets plooped right there. And then we're weighting that by our joint density function. So I'm going to get really nuts and use 3 different colors and say that, okay, that is our joint density. So that's getting put here. And then we do the double integral. Much like finding probabilities, it does not matter whether you do dy dx or dx dy. I chose to do dy dx. And so that means that my inner integral is going to go from 0 up to x. After I integrate out y, all of this gets collapsed onto the x-axis. And so then I'm going to integrate x from 0 to 1. Again, I used ChatGPT to find this. I'm not going to show it this time because we've done it in some other videos, but you could use whatever technology you like and figure out that the answer to that double integral is 1/6. So the expectation of x times y is equal to 1/6. We'll do a few more examples. So the nice thing about this is that not that much is going to change from example to example if you have the same joint density. And what I mean by that is finding the expectation of 3xy We don't have to think about the bounds of the integral again, so they'll always just be the same. The only thing that's different is instead of g of xy being equal to xy, I'm putting in 3xy there. And then I am still weighting by 1 over x, dy dx. And if you compute that, that turns out to be 1/2. I'm scrolling back up to our properties, and you should notice that one of these properties actually lets us do this with a shortcut. In particular, this first property says that if we have a constant, we could move that constant out of the expectation. And so I'll say here with property 1, e of 3xy, c is equal to 3, so that's our constant. That's going to be equal to 3 times the expectation of x times y, and that is equal to 3 times 1/6, which is still 1/2. So that property checks out, at least for this particular example. Now we'll figure out, just to have an example of a different expectation, the expected value of y divided by x. Again, it's the same joint density, so I don't have to rethink about my bounds, which is really, really nice. The only thing that changes is we're plugging in y over x for our g of xy. Everything else is the same. And again, you could use technology to figure out that this expectation turns out to be 1/2. And one final example, because why the hell not? We could figure out the expectation of something a little more complicated, like 3 times x times y plus y divided by x. That, again, it's the same joint density, so I don't have to rethink the bounds. The only thing that changes is what gets plooped in first, which now is 3xy plus y over x. Everything else is exactly the same, so nothing too different from the previous examples. And if you calculate this out with either by hand, which I don't recommend, or by some sort of technology, which I do recommend, you wind up with an answer of 1. Going back up to our properties, this second property we could have actually used that as a little bit of a shortcut for that last example. That says the expectation of adding two different functions of x and y together. You could split that up and find the expectation of each component of the sum separately. And so how that would work for this example, what that means is that the expectation of 3xy plus y over x, we could have used a shortcut and said that that is the expectation of 3xy plus the expectation of y over x, and we had already computed those two things to be 1/2. So that's 1/2 plus 1/2, 1, and we get the same exact answer. So again, bivariate expectation isn't anything too different from what we've been doing. So we're still setting up a double integral. It also has a lot of the same types of properties as some things with univariate expectation had, like particularly this first property about the constant looks similar to something that we had in a previous section, which is really nice. We'll talk about these other two properties in class, but for now you have enough to jump over to this week's class prep quiz.